My name is Carl Grace again, and I'm going to talk a little bit about custom ASICs for high-energy physics and why custom ASICs are an enabling technology for new advances in particle and high-energy physics, as well as nuclear science and energy science and a lot of different areas. And I'm at Lawrence Berkeley National Laboratory. All right, so I know not a lot of people are always very familiar with Lawrence Berkeley Laboratory. Of all the U.S. national laboratories, we are the most diverse scientifically in that we do a lot of different kinds of science. Any much kind of science you can imagine, we do it at LBL. In terms of, we start with physical science, and then there's computing, bio, earth sciences, and all kinds of stuff. We're pretty large. We're 3,500 employees and about 1,000 students at any given time, and roughly 1,750 visiting researchers a year. We operate a number of national user facilities, which means that these are science facilities that scientists from around the country and around the world can come to LBL to do their science, including energy light sources called the Advanced Light Source, a supercomputer center, Joint Genome Institute, and so on. And there's been 16 Nobel Prizes earned for work from Lawrence Berkeley National Laboratory. The latest was in 2020 for the CRISPR gene editing technology. And just a little fun fact, at LBL you can write me a letter in elements. So you could write me a letter and address it to Carl Grace at Lawrencium, Berkeleym, Californium, Aramecium. And all these elements were discovered at Lawrence Berkeley National Lab, along with 12 others, the most famous being plutonium, of course, and we also invented that radiation symbol that everybody knows and loves. All right, so now on to my talk. So the point of my talk is science. So how do we study the universe? And probably the best way to study something is to look at it. But there's a problem, and there's a basic fact in science called the Rayleigh criterion, which means that to see features in whatever you want to see, you need to probe it with something that is smaller than what you want to see. So for example, if in the case your probe is smaller than those peaks, you can resolve both the peaks. In the case that the probe is larger than the peaks, you can see that you lose the two peaks. And the Rayleigh criterion is kind of where you balance them. So the point here is that you need to have a smaller and smaller probe to look at things that are smaller and smaller. So how does that actually work out in practice? Well, in biology, you typically want to look at things that are 10 to the minus 6 or a micron in scale, roughly. And luckily, that turns out to be similar to the wavelength of light. So you can use visible light to do a lot of biology. And that's why visible microscopes are typically what is used for biological science. But what if you want to look at smaller things? Well, you can't use visible light anymore. So what do? Well, if you're in chemistry or material science, you're typically looking at things that are more on the nanometer scale. In that case, you want to use electrons. And that's because due to the de Broglie wavelength, where basically every particle is also a wave, you can use that wavelength as your light, essentially. And you can use it as an electron microscope, and it can go down about 3 orders of magnitude smaller than visible light. And in terms of the energy needed to do that, it's in the kiloelectron volt. And an electron volt is the amount of energy it takes to accelerate one electron by 1 volt. And so it's the way we use in physics to keep from having really small numbers of joules. So what if you want to get something much smaller? So we're at the nanometer scale, but the nucleus of an atom itself is about 10 to the minus 15. A nucleus can be 100,000 times smaller than that. So what do? Well, we use a more higher energy probe, and in this case, we use a hadron. You've heard Large Hadron Collider. The hadron, all that means, it's not rocket science. All a hadron means is it's a particle that's composed of quarks. And so the simplest hadron is a proton, and that's actually what's used in the LHC. And that can get us another 9 orders of magnitude down from an electron microscope. As you can see, this is the Large Hadron Collider. This is the area around Geneva in Switzerland. The collider is 300 feet underground. I'll talk about it more. And these are just some pictures of one of the detectors. And so a little more detail. So ATLAS is one of the 2 main detectors at the LHC. There's a couple of others as well. And so thinking about the LHC, or the Large Hadron Collider, as a microscope is pretty useful because it puts it into context where, remember, a typical microscope is a light source and a camera. The best microscopes are when you get the brightest light and you get the highest resolution camera. And our kind of microscope is the collider is the light and the detector is the camera. And the best microscope there is for doing this in the world right now is the LHC at CERN, which is in Switzerland, and it actually crosses the French border. This white circle is 300 feet underground. It's 27 kilometers in circumference. You can see someone riding by this pipe, and the pipe is filled with all kinds of cryogenics and vacuum pumps and so on. The actual proton beam flows in a pipe that's inside that of about 5 millimeters in diameter. So it's very well controlled, and magnets are used to spin it around in this curve. The ATLAS detector, which is where the two proton beams, which are going in opposite directions, interact, is located 300 feet under here. And so what does it do? Well, this is the ATLAS detector. To give you a sense of scale, these two things on the ends here are called the end caps, and they're also sensors of different kinds. And these are the two end caps of the ATLAS detector during construction. So you can see how small the people are. So it's a very, very large facility. And so what does it actually do? Well, it takes snapshots of collision events. So there's two beams of protons going in opposite directions at a very, very, very close to the speed of light. So they have a lot of kinetic energy. When they interact here, they make essentially an explosion. And I'm sure you've all heard Einstein's mass energy equivalence equals mc squared. If you have two particles that have a lot of energy and they interact, that energy can also be turned into new matter. And that's actually exactly what happens. So we have a huge number of various kinds of particles that are basically created out of thin air because of the high kinetic energy of this proton collision. And this is actually some data of one of these collisions, and you can see the two proton beams interacting, and you can see all the junk that's created. And so how do we read all that stuff out? Well, we have to do it using a large number of sensors and custom integrated circuits. So the question is pretty obvious. Well, why are you designing custom integrated circuits for high energy physics? Why don't you use image sensors that are commercially available and so on? It's because there are some unique challenges for custom ASICs for physics. And primarily those are because in physics we're often operating in extreme environments. The most well-known is a high radiation environment. One of the consequences of these large collisions is that there's a lot of radiation around. There's also a lot of experiments right now that are using cryogenics. For example, this is what's called a liquid argon time projection chamber, where it's a sensor where the liquid argon is used as the detector, but liquid argon is roughly minus 200 degrees C. So you can't use commercial off-the-shelf electronics for that. You have to custom design them for low temperature. And you also have some issues with vacuum for getting heat out and so on. So typically, many of these experiments require custom ASICs. So to go into a little bit more detail about some of these requirements, the main one is radiation that I'll talk about because I'm really focusing here on ATLAS. So there's two main types of radiation damage that concern physicists. And it's single event latch-up and single event transients turn out to be less important. So we're really focused on total integrated dose. That means the buildup of damage to the silicon substrate over time. And we're looking about single event upsets where a deposition of energy can actually flip a bit somewhere in your system. And so here's an example of a total integrated dose failure. You have your poly, your insulator, and your silicon. If you have say a photon deposit energy there in the silicon dioxide, because this is under electric field, the charges are separated and they can get trapped at the interface here. And if they get trapped at the interface here, when you want to operate the device, you have to raise the voltage a little bit to compensate for those holes, which is equivalent to an increase in the threshold voltage. Over time, that can cause the device to fail. In modern technologies, this isn't much of an issue because the insulators are so thin that excess charge can tunnel away. But then you have the problem where you start getting substrate damage, where you get interstitials in the substrate that can lead to leakage currents, which can also cause your device to fail over time. The single event upset's a little bit different in that you have a particle depositing energy inside the substrate, and then because we're typically using some kind of drift mechanism to collect the charge that we want, it also collects the charge that we don't want. And so you can get enough energy here that the bit can flip. It turns out that as the devices get smaller, this becomes more of a problem because the amount of energy that you need in order to get a significant voltage change goes down because Q, the charge, equals CV. So the reason why there's so much effort in custom ASICs is that the radiation requirements for high energy physics experiments far exceed any commercial applications. Here on the x-axis, we have the amount of radiation in terms of rads, and you can see low Earth orbit satellites typically have to operate up to around 100 kilorad of total dose. Deep space probes that aren't protected by the atmosphere have to go, 2 or 3 or 4 megarads. The LHC, which is the currently operating machine in Switzerland, requires about 50 megarads of radiation tolerance. And the new upgrade, the HL stands for high luminosity, which means that the amount of protons per given time in the beam is going to go up, is going to need up to a gigarad of total integrated dose. And the reason that it needs such high radiation tolerance is that replacing the ASICs is a very time-consuming and expensive operation. The entire experiment needs to be shut down, the detector needs to be disassembled, new ASICs need to be put together and reassembled, and that can take 6 months. And so by extending the lifetime of the custom ASICs, you're enabling the scientists to get more science done. In terms of single event effects, you can see that the problem you're going to get can vary quite a bit depending on what the actual, what is actually depositing energy. And so we're particularly concerned about heavy ions and protons, which are created inside the collisions. And so, and the reason we're concerned about them is they generate large clouds of electron-hole pairs. So how do we deal with that? Well, there's a couple of main ways. The first main way is called triple modular redundancy, or TMR, and this is pretty universal in these kinds of custom integrated circuits. Basically what you do is that you triplicate all your logic, and then you have latches and use a majority voter circuit to then decide which is the actual correct answer. What's hard about triple modular redundancy, besides the obvious fact that it creates a lot of overhead, is that it's not always obvious at what level you should do redundancy. Do you make 3 of every gate? Do you make 3 of every circuit? Do you make 3 of every module? It's not always clear. Also, if you have a situation where you have heavy ions, this cloud can extend over a significant amount of space, which means that say you had 3 adders in parallel. You need to make sure that they're physically spaced remote from each other so that you don't have multiple of your adders getting hit by the same heavy ion, which has been a problem in the past. Also, increasingly, analog circuits are starting to have problems with this, which wasn't always the case in the past, so that's a new thing. Another thing that they do in the chips for Atlas is continuous reconfiguration. So basically, there will be a certain rate at which you will have single event upsets regardless of your TMR solution. And so they're particularly bad when it happens to a configuration, a static configuration register. So what's done in practice is that the chip is continuously reconfigured so that the amount of time at which during it's misconfigured is minimized. So moving closer in, this is a picture of the Atlas inner tracker. And so the inner tracker is exactly, here is the position here where the beams interact, so the collisions are right here. This is a cutaway, so it actually goes full 360 around, and it's called pixel barrels. And there's an inner layer and an outer layer. The idea is if you have multiple layers of these sensors, then you can actually calculate the momentum of the particles because the curves bend when they are in a magnetic field. So how do these sensors get made? Well, there's 2 ways to make these. There's one where you do it kind of like a digital camera, where the actual sensor is in the same chip as the readout. But for Atlas, they use what's called a hybrid pixel, where you have a passive silicon sensor chip, which is essentially an array of reverse bias diodes. Then you have a readout chip, which basically has a small amplifier, a time digital converter, and an ADC in it. And then by having them in separate chips that are then bonded face to face, you're able to optimize the performance because you can implement the sensor in a different technology from the readout chip. And so here's how it looks like. You get a particle track, it generates an electron-hole pair cloud in the pixel semiconductor that gets drifted to this bump, and then the bump goes into the front-end chip. And here's a picture of the latest chip for the high luminosity or high lumi upgrade. This one's called RD53, and it's because it's for the 53rd R&D campaign from CERN, but now it's called ITK PIX or Inner Tracker Layer PIX. And here's a picture of the layout, which is it's done in an analog island in a sea of layout. Remember, every pixel has an analog core, and then there's a lot of digital processing in order to do data sparsification and that kind of thing. And so this is a more commercial design methodology than has typically been done for high-energy physics because of the demanding requirements of this application. You can see here these are 4 pixels, and then they're embedded in a sea of digital. And the entire ITK has 13 square meters of active area, or 1.4 billion pixels. So it's a very large device. And here is, which is pretty cool, this is a actual event that's been reconstructed from data from this chip that's showing the creation of a Higgs boson. And this was on a certain date and time. And you can see that the Atlas and CMS detectors, which were 2 detectors, were instrumental to the Nobel Prize in Physics in 2013, which is the discovery of the Higgs boson. And just it's kind of an interesting aside, the Higgs boson was kind of the last part of the standard model of physics, and so people were very concerned that the evidence was as solid as possible. So Atlas and CMS were two different experiments that were done completely isolated from each other, and they agreed with each other to within 6 sigma. So it's a pretty solid result. So how did we, as a bunch of small research institutes, able to develop this integrated circuit? And the way we did it is we partnered with some other institutes, and we had to figure out a way in order to share our design files and everything. And so we led the design of this at Berkeley Lab. We also worked with University in Bonn, which is in Germany, and NICEF, which is in Amsterdam. We also worked with Genova in Italy and CPPM in France. And so we were looking at the beginning of this project about 20 years ago. We were looking at, well, how are we going to share design data, which was not really well defined at the time. And we found SOS, and it turns out we were the first academic customer of SOS, and now that's a standard across the high-energy physics community. And this way, we were able to have our own copies of PDKs, and we all did Virtuoso, and Bonn and Berkeley did all the RTL and the implementation, and then the testing and PCB design was spread out, and all the documents were spread out and able to be shared. And we even though we could use Git for RTL, we found that using SOS was helpful because it kept everything in one place, and all someone had to do was an update, and then we fully had access to everything. When we were using SOS, we had our IPs local to Berkeley, and then we had Bonn, and we had NICEF, and we were able to cache data from each other. So we weren't always sending data all the time. And it's also very helpful because we had very, very different computing infrastructures, say at NICEF, Berkeley, and Bonn, and it was completely transparent because we just use SSL, to bring all the data around. So we didn't have to deal with all the permissions and all the that kind of stuff. So I'll give you a final thought. So physicists started making chips in the 80s, and at that time it was a physicist drawing some transistors, kind of like a hobby project. Then in the 90s, it got complicated enough that the various institutes, Berkeley Lab as being one of them, started developing integrated circuit design teams, and they were really analog focused, and the digital was minimized as much as possible. Then in the 2000s, about 20 years ago, we started doing these big projects because the LHC required them. And this is FEI4, which was the big one. And you can kind of see this is sort of done in a kind of an old-fashioned style where we had pixel arrays, and then we had the digital next to them, and then a big digital block at the bottom. And the team started getting bigger. Then when we did the current version, which I just showed you, we used commercial design styles, validation, version control, all that stuff, and we got a billion transistor chips that worked the first time. And you can see the design teams are getting pretty big. This is at a meeting at CERN in Switzerland because the teams are all over North America and Europe, and you can see it looks more like a commercial chip now. So what's the future hold? I think with a lot of these new technologies, maybe it'll be somebody writes a few lines of Python, and the next custom ASICs will come out. Thank you for your attention.